Hello, and welcome to the deep somna. Maybe the night feels long. Maybe thoughts are drifting in circles, refusing to settle. Or maybe there's simply a pull towards something larger than the small concerns of the day. Something vast enough to dissolve the edges of worry and leave only quiet wonder in its place. Tonight, the journey begins not with answers, but with the absence of them. With the kind of question that opens rather than closes, that expands rather than resolves. What was there before anything was there? The question itself seems to fold inward, collapsing under its own weight, because to ask what came before requires time, and time may be precisely what didn't exist yet. To ask what was there requires space, and space may have been waiting to begin. Science approaches this edge carefully, the way someone might approach the rim of a cliff in fog, knowing that solid ground gives way to something else just ahead. The tools we use to understand the universe, mathematics and observation, measurement and reason, all depend on the universe already being in motion. They describe change, process, becoming. But the moment before becoming, that lies beyond the tools themselves. Still, the urge to look remains. To peer back through time, through the expanding fabric of space, through the cooling and clustering of matter, all the way to the first instant that can be described, not to find a definitive answer, but to trace the story as far as it goes before the story dissolves into something else, into speculation, into metaphor, into the peculiar silence that sits at the foundation of everything. The universe, as far as observation can tell, is not standing still. Galaxies are moving away from one another, not because they're traveling through space like ships across an ocean, but because space itself is stretching. The distance between things is growing, and that growth is measurable, consistent, relentless. This wasn't always obvious. For a long time, the cosmos seemed eternal and unchanging, a fixed backdrop against which stars burned and planets turned. The idea that the entire stage itself might be shifting, that the very dimensions of reality might be in flux, felt too strange to accept easily. But observation doesn't care about comfort. It simply reports what is. And what is, according to the light from distant galaxies, is expansion. Light traveling across vast distances carries information about its source. When that light is stretched, shifted toward longer wavelengths, it indicates motion away from the observer. And the farther the source, the more the light is stretched. A pattern emerges. Distance correlates with speed. The universe is not static. It's unfolding. If everything is moving apart now, then logically, everything was closer together in the past. Rewind the expansion, and the galaxies draw nearer. The space between them shrinks. Matter becomes denser. Temperatures rise. Go back far enough, and the entire observable universe, all the galaxies and stars and planets and gas and dust, would be compressed into a region smaller than a solar system. Smaller than a planet. Smaller than an atom. This is the foundation of what gets called the Big Bang, though the name suggests something it wasn't. There was no explosion in the usual sense. No debris flying outward from a center point, because there was no center. There was no outside. Space itself was what was beginning, expanding in all directions simultaneously, creating room for matter and energy to exist within. The Big Bang isn't the moment of creation in some absolute sense. It's the earliest moment we can point to with any confidence. The beginning of the universe as a process we can describe. What lies before that moment, or whether before even makes sense in that context, remains open. At the very earliest edge, in the first incomprehensibly brief fraction of a second, conditions were so extreme that the usual rules break down. This period is sometimes called the Planck epoch, named for the physicist who first described the scales at which quantum effects and gravity both become important. Imagine the entire observable universe compressed into a volume smaller than a proton, temperatures so high that no particles as we know them could exist. Energy so dense that space-time itself fluctuates wildly, foaming and twisting at scales far below anything we can observe. In this state, the four fundamental forces, gravity, electromagnetism, the strong nuclear force and the weak nuclear force, may have been unified. Not merely coexisting, but indistinguishable, aspects of a single underlying reality. A symmetry that would soon break, allowing the forces to separate and take on distinct identities. But this is speculation built on mathematical frameworks that haven't been fully tested. We have no theory of quantum gravity, no way to describe how space-time behaves when quantum mechanics and general relativity both matter equally. So the Planck epoch remains a boundary, a horizon beyond which the story fades into conjecture. After that earliest instant, as the universe expanded and cooled, the forces began to split off from one another. Gravity separated first, becoming the force that would shape the large-scale structure of the cosmos. Then the strong force diverged, the one responsible for binding quarks into protons and neutrons. Finally, electromagnetism and the weak force, which had been unified as a single electroweak force, separated into distinct phenomena. Each transition was smooth, inevitable, driven by the cooling of the universe, in the same way that steam condenses into water as temperature drops. With each separation, the universe became more complex, more structured. New possibilities emerged. Particles that couldn't exist at higher energies became stable. Interactions that had been forbidden by the symmetry of the unified force became possible. And then, in a span of time, almost too brief to comprehend, something extraordinary happened. The universe didn't just expand, it inflated. In far less than a second, perhaps in a trillionth of a second, the fabric of space itself stretched exponentially. Not because anything was moving through space, but because space was growing faster than light could cross it. Imagine a grain of sand suddenly becoming larger than a galaxy. That's the scale of inflation. A region of space smaller than an atom ballooned to a size larger than the observable universe we see today. Why this happened is still debated. One possibility is that space was filled with a field, a kind of energy that doesn't dilute as space expands. Instead of thinning out, this energy remained constant, driving faster and faster expansion. This field, often called the inflaton, existed in a high-energy state. It was unstable, temporary, but while it lasted, it dominated everything. And when it finally decayed, when the field transitioned to a lower energy state, all that stored energy was released. The universe was flooded with particles and radiation. This is sometimes called reheating, the moment when the cold, rapidly expanding void was suddenly filled with heat and motion. From that point forward, the universe was no longer just geometry. It was matter. It was energy. It was light. Inflation explains several puzzling features of the cosmos. Why, for instance, the universe looks so uniform in all directions? If regions of space that are now on opposite sides of the sky were once close together, close enough to reach equilibrium before inflation separated them, then it makes sense that they would have similar properties. Inflation also explains the tiny ripples in density that would later grow into galaxies, quantum fluctuations in the inflaton field, microscopic variations in energy density, were stretched to cosmic scales during inflation. Those variations became the seeds of structure, the slight differences in density that gravity would amplify over billions of years. But inflation is still a theory. A well-supported theory, consistent with observations, but not yet proven beyond doubt. There are alternatives, other ways to explain the uniformity and structure of the universe. The search for definitive evidence continues. After inflation ended and the universe was flooded with energy, particles began to form. Quarks and antiquarks, leptons and antileptons, photons and gluons, all appearing and annihilating in a dense, hot plasma. This was a chaotic time. Particles collided with tremendous energy. Pairs of particles and antiparticles formed from pure energy, then annihilated back into energy a moment later. But something subtle happened here, something that didn't have to happen, but did, for reasons still not fully understood. There was a slight imbalance. For every billion antiquarks, there were 1,000,001 quarks. For every billion positrons, 1,000,001 electrons. Just one extra particle of matter for every billion pairs. A tiny asymmetry, almost negligible. But when the annihilations were over, when every particle of antimatter had found a partner and vanished in a flash of energy, that one leftover particle remained. And from that surplus, everything was built. Every atom in every star, every molecule in every planet, every cell in every living thing. All of it traces back to that minuscule excess of matter over antimatter. Why the imbalance existed is one of the deepest unsolved problems in physics. The laws governing particles seem to treat matter and antimatter almost identically. Almost, but not quite. There are subtle differences, violations of symmetries, that physicists call CP violation. These violations have been observed in laboratory experiments. Certain particles decay in ways that favor matter over antimatter, but only slightly. Not enough on their own to explain the imbalance we see. Perhaps there were other particles in the early universe, heavier and short-lived, that decayed asymmetrically. Perhaps the conditions during the first moments were such that matter production slightly outpaced antimatter production. Or perhaps the answer lies in physics we haven't discovered yet, in interactions we haven't observed, in symmetries we haven't uncovered. For now, the imbalance remains a clue without a full explanation. A reminder that the early universe holds secrets we haven't unlocked. After the matter-antimatter annihilation, the universe was left with a sea of particles. Quarks, electrons, neutrinos, photons, all moving at tremendous speeds, colliding, interacting, but not yet combining into stable structures. The temperature was still too high. energy was too great. Anytime quarks tried to bind together into protons or neutrons, the surrounding radiation had enough energy to break them apart again. But as the universe continued to expand, it continued to cool. And eventually, the temperature dropped low enough for protons and neutrons to remain stable. This happened about 1 second after the beginning. In cosmic terms, almost immediately. In human terms, an eternity of processes compressed into a single tick of a clock. With protons and neutrons now stable, the next step could begin: fusion. In the intense heat, protons and neutrons collided and stuck together, forming the nuclei of light elements. A proton and a neutron combined into deuterium. 2 deuterium nuclei fused into helium. A tiny fraction formed lithium. This process, called Big Bang nucleosynthesis, lasted only a few minutes. The universe was cooling rapidly, and soon the temperature dropped below the threshold needed for fusion. By the time the universe was about 20 minutes old, nucleosynthesis was over. The ratio of elements was set. Roughly 3/4 hydrogen nuclei, 1/4 helium nuclei, and trace amounts of deuterium and lithium. That ratio persists today. The oldest stars, the ones formed from gas that has never been processed through previous generations of stars, have compositions that match the predictions of Big Bang nucleosynthesis almost perfectly. It's a remarkable confirmation. The chemistry of the universe, the basic ingredients from which everything else would be built, was determined in the first few minutes. But even though nuclei existed, atoms did not. Not yet. Electrons were still moving too fast, too energetically, to be captured by nuclei. And photons, particles of light, were constantly interacting with those free electrons, scattering off them in endless collisions. The universe was opaque. Light couldn't travel far. It was trapped in a dense fog of charged particles, bouncing from electron to electron, never making any real progress. This would continue for a long time, hundreds of thousands of years, during which the universe simply expanded, cooled, and waited. Stars had not yet formed. Galaxies did not exist. There was no structure, no differentiation, just a smooth, nearly uniform sea of hydrogen and helium nuclei, electrons, and photons. But the universe was not perfectly uniform. The tiny density fluctuations seeded during inflation were still there, subtle variations in how tightly packed matter was in different regions. These variations were small, differences of only 1 part in 100,000. But they were real and they mattered. Regions that were slightly denser had slightly more gravity. They pulled on surrounding matter, drawing it inward. Slowly, imperceptibly, these regions began to grow denser still. Meanwhile, the less dense regions emptied out as matter drifted toward the denser zones. The universe was beginning to develop texture, contrast, the early hints of structure. But this process was slow. Gravity is a weak force. It takes time to amplify small differences into large ones. And for now, the universe was still too hot, too energetic, for gravity to fully take hold. The radiation pressure, the outward push from photons bouncing off particles, was strong enough to resist gravitational collapse. Everything was in balance. Matter wanted to clump together. Radiation wanted to spread it apart. The two forces held each other in check. And so the universe drifted forward, cooling degree by degree, expanding steadily, waiting for the moment when the balance would tip. That moment came roughly 380,000 years after the beginning. By then, the temperature had dropped to about 3,000 degrees. Still hot by everyday standards, but cool enough for something crucial to happen. Electrons, which had been zipping around freely, began to slow down. And as they slowed, they were captured by the nuclei of hydrogen and helium, forming neutral atoms. This transition is called recombination, though the term is misleading. The electrons and nuclei had never been combined before. This was the first time atoms existed in the universe. And with the formation of neutral atoms, the fog lifted. Photons no longer had free electrons to scatter off. They could travel unimpeded through space. For the first time, the universe became transparent. Light that had been trapped for hundreds of thousands of years was suddenly released, streaming outward in all directions. That light is still traveling today. Stretched by the expansion of space, shifted from visible light down into the microwave part of the spectrum, cooled to just a few degrees above absolute zero. This is the cosmic microwave background, the oldest light we can see, a direct image of the universe as it was 380,000 years after the beginning. When instruments sensitive enough to detect this faint radiation were developed, they revealed something astonishing. The glow was almost perfectly uniform, nearly the same temperature in every direction. But not quite. There were tiny variations. Fluctuations of just a few millionths of a degree. Patches of sky that were slightly warmer or slightly cooler than the average. These fluctuations correspond to the density variations in the early universe. Warmer regions were slightly less dense. Cooler regions were slightly denser. And those denser regions, the cooler patches, were the places where matter was beginning to clump together under gravity. The seeds of galaxies. By studying the pattern of these fluctuations, cosmologists can learn an enormous amount. They can measure the age of the universe, the rate of expansion, the density of matter. They can determine how much of the universe is ordinary matter, how much is dark matter, how much is dark energy. The cosmic microwave background is a treasure trove of information. A snapshot of the universe in its infancy, before stars, before galaxies, before any of the complexity we see today. And it marks the furthest we can see directly. Anything earlier than recombination is hidden behind the opaque fog of the early universe. To probe deeper into the past, we need more than light. We need other messengers. Gravitational waves, perhaps, or neutrinos, particles that barely interact with anything and could have traveled freely even in the earliest moments. But for now, the cosmic microwave background is the boundary of direct observation, the edge of the visible past. Beyond it lies inference, theory, mathematical models that extend the story backward toward the Planck epoch and the beginning itself. After recombination, after the light was freed, the universe entered a new phase, one without much illumination. The photons from the Big Bang were still there, but they were fading, stretching, cooling into invisibility. And no new sources of light had yet appeared. There were no stars, no galaxies, just vast clouds of neutral hydrogen and helium drifting through expanding space. This period is often called the cosmic dark ages, not because anything ominous was happening, but simply because there was no light. If someone could have existed then, floating in the void, they would have seen nothing. No stars to navigate by, no glowing nebulas, no distant galaxies, just darkness. And yet, beneath that darkness, gravity was working. Patiently, relentlessly. The density fluctuations that had been imprinted during inflation, that had been visible in the cosmic microwave background, were growing stronger. Regions of space that were slightly denser pulled in more matter. As they grew denser, their gravity increased, pulling in even more matter. A runaway process, slow at first, but accelerating over time. Clouds of hydrogen gas, diffused and scattered, began to collapse inward. They formed clumps, then larger clumps, then deep gravitational wells. And at the centers of these wells, pressure and temperature began to rise. The gas was being compressed. Atoms were colliding more frequently, more violently. The kinetic energy of their motion was converting into heat, deep within the densest clouds. Conditions were approaching a threshold, a temperature and pressure at which hydrogen nuclei, normally repelled by their positive electric charges, could be forced close enough to fuse. This process takes time. Millions of years. Gravity pulls slowly, gas heats gradually. The threshold approaches step by step. But eventually, inevitably, fusion began. Hydrogen nuclei collided and merged, releasing energy in the process. That energy pushed outward, creating pressure that resisted further collapse. A balance was struck. Gravity pulling inward, fusion pushing outward. The cloud stopped collapsing and began to shine. A star was born. The first stars were different from most stars that exist today. They formed from pure hydrogen and helium, with no heavier elements. And because of this, they could grow much larger. These primordial stars, sometimes called population the third stars, may have been hundreds of times more massive than the sun, burning fiercely, intensely hot, radiating enormous amounts of energy. They lived fast. Fusion in such massive stars proceeds at a furious rate, consuming fuel in just a few million years, a blink in cosmic terms. But while they lived, they transformed their surroundings. The light they emitted, especially ultraviolet radiation, was intense enough to ionize nearby hydrogen atoms. Electrons were stripped away, and the neutral gas reverted to a plasma. This process, called rionization, spread gradually across the universe. Each new star created a bubble of ionized gas around itself. As more stars formed, the bubbles expanded and merged. Over hundreds of millions of years, the neutral hydrogen that filled space was ionized again. The fog that had returned after recombination was cleared away once more. The cosmic dark ages were ending. Light was returning to the universe. But this light was different from the glow of the early universe. It was localized, concentrated in stars and the regions around them. It was structured, marking the places where gravity had succeeded in pulling matter together. The universe was no longer smooth. It was beginning to develop texture, contrast, regions of brightness and darkness, and the first stars did more than just shine. They also created. Inside their cores, hydrogen fused into helium, helium fused into carbon, carbon into oxygen, oxygen into neon, neon into magnesium, and so on, climbing the periodic table step by step. Each fusion reaction released energy, but it also built heavier elements, elements that did not exist in the early universe, elements that would become essential for planets, for chemistry, for life. When the most massive of these first stars exhausted their fuel, they didn't fade quietly, they exploded. Supernovae, catastrophic events that briefly outshine entire galaxies. In those explosions, even heavier elements were forged. Iron, nickel, gold, uranium. All the elements heavier than helium owe their existence to processes inside stars or during supernova explosions. The debris from these explosions scattered across space, mixing with the surrounding gas. The next generation of stars, forming from clouds enriched by supernova remnants, were no longer pure hydrogen and helium. They contained traces of heavier elements. And those elements changed how stars formed, how they behaved, and what could exist around them. Rocky planets could form because there was now silicon and iron and magnesium. Complex chemistry could begin because there was now carbon and oxygen and nitrogen. The universe was becoming richer, more diverse, more capable of producing complexity. Stars began to cluster together. Dozens, then hundreds, then thousands of stars, all bound by their mutual gravity. These clusters were the seeds of galaxies. Over time, they merged, collided, grew larger. Gas clouds drawn together by gravity collapsed and formed new generations of stars. The process repeated, building up larger and larger structures. Some galaxies grew into elegant spirals, disks of stars rotating around a central bulge. Others became elliptical, their stars moving in random orbits, forming a smooth, football-shaped distribution. Still others remained irregular, chaotic, shaped by collisions and interactions with neighbors. And everywhere, woven through and around these galaxies, was dark matter. Invisible, but essential. Dark matter doesn't interact with light. It doesn't emit photons. It doesn't absorb them. It doesn't reflect them. It's completely transparent to electromagnetic radiation, but it has mass. And mass creates gravity. And that gravity shapes the motion of everything around it. When astronomers observe galaxies rotating, they notice something odd. Stars on the outer edges of galaxies are moving faster than they should be, based on the visible matter alone. If galaxies contained only the stars and gas we can see, those outer stars would fly off into space. The gravity from visible matter isn't strong enough to hold them, but they don't fly off. They stay in orbit, held by additional gravity from something we can't see. That something is dark matter. It forms halos around galaxies, extending far beyond the visible stars. It provides the gravitational scaffolding that holds galaxies together. Without dark matter, galaxies wouldn't exist. The gas clouds that collapsed to form stars would never have become dense enough. The structures we see today wouldn't have formed. Dark matter outweighs ordinary matter by a factor of 5 or more. It's the dominant form of matter in the universe. And yet, we don't know what it is. Physicists have searched for dark matter particles in underground detectors, in particle accelerators, in space-based telescopes. They've looked for signs of dark matter annihilating, decaying, interacting in any way that would reveal its presence. So far, nothing definitive. Dark matter remains elusive, detectable only through its gravitational effects. As galaxies formed and evolved, they didn't scatter randomly through space. They followed patterns, tracing out vast structures, filaments of galaxies, stretching across hundreds of millions of light years. Sheets and walls, thin but extensive. Great voids. Regions almost devoid of galaxies. This cosmic web is shaped by dark matter. The filaments trace the densest regions of dark matter where gravity is strongest. Galaxies form where the filaments intersect, where matter is concentrated. The voids are regions where dark matter is sparse, where gravity is weak, and where galaxies are rare. This structure was imprinted early, during inflation, as tiny quantum fluctuations. Those fluctuations grew under gravity, amplified over billions of years, until they became the large-scale structure we observe today. The universe, once nearly uniform, has become richly textured. Galaxies cluster together in groups and superclusters. Voids separate them. The cosmic web stretches across space, a network of light and darkness, and through it all, the expansion continues. Space keeps stretching, carrying galaxies apart, thinning the web, increasing the distances between structures. For most of the universe's history, this expansion was slowing down. Gravity from all the matter in the cosmos was pulling everything back together, resisting the expansion. The expansion continued, but at a decreasing rate. It seemed inevitable that eventually, the expansion would slow to a crawl or even reverse. But then, late in the 20th century, astronomers studying distant supernovae made an unexpected discovery. The expansion isn't slowing down, it's speeding up. Something is causing the universe to expand faster over time. Something that acts like a repulsive force, pushing space apart. That something is called dark energy, and it makes up roughly 70% of the universe. Dark energy is even more mysterious than dark matter. We don't know what it is. We don't know why it exists. We don't even know if it's constant or changing over time. One possibility is that dark energy is simply a property of space itself. A baseline energy that exists everywhere, even in what we think of as empty vacuum. Einstein's equations allow for this. In fact, Einstein himself introduced a term, the cosmological constant, to represent such an energy. If space has an intrinsic energy density, then as the universe expands and more space is created, the total amount of dark energy increases, and that would cause the expansion to accelerate. But when physicists try to calculate what this energy density should be, based on quantum mechanics, they get an answer that's wrong by an absurd margin. More than 100 orders of magnitude. Either quantum mechanics is deeply flawed in ways we don't understand, or something else is at play. Another possibility is that dark energy is a field, something that changes over time, like the inflaton field that may have driven cosmic inflation. If if that's the case, then dark energy might not remain constant. It might strengthen or weaken or behave in unpredictable ways. And the future of the universe depends on which of these possibilities is correct. If dark energy remains constant, the universe will expand forever, growing colder and emptier. Galaxies will drift apart. Stars will burn out. Eventually, the cosmos will fade into darkness. If dark energy strengthens, the expansion could accelerate so much that even galaxies, stars, and atoms are torn apart. This scenario is called the Big Rip. If dark energy weakens, the expansion might slow, or even reverse, leading to a collapse back into a hot, dense state. A big crunch. We don't know which future awaits. The answer lies in understanding dark energy, and that understanding remains beyond our reach. For now, the universe continues to expand, accelerating gently, driven by a force we can measure but not yet explain. Galaxies drift farther apart. The cosmic web stretches thinner, and the night sky, over billions of years, will slowly grow emptier as distant galaxies slip beyond the horizon of what light can traverse. But that future is still far away. For now, the universe remains full of activity, full of light, full of the slow processes that shape stars and galaxies and the structures between them. Stars continue to form in dense clouds of gas and dust. Gravity pulls matter together until fusion ignites. And each new star joins the vast population that already exists, scattered across billions of galaxies. Not all stars are alike. They come in different sizes, different temperatures, different colors. The most massive burn hot and blue, consuming their fuel rapidly. The smallest burn cool and red, sipping their fuel so slowly they might shine for trillions of years. Our own sun falls somewhere in the middle. An average star, neither particularly large nor particularly small, burning hydrogen in its core at a steady, sustainable rate. It has been shining for about 4.6 billion years. And it will continue to shine, relatively unchanged, for another 5 billion years or so. But eventually, even the sun will exhaust its hydrogen. When that happens, fusion in the core will cease. The core will contract under its own gravity, heating up as it does. That heat will cause the outer layers to expand. The sun will swell into a red giant, growing large enough to engulf the inner planets. Mercury, Venus, possibly Earth, all consumed by the expanding outer envelope of the dying star. This phase won't last long, cosmically speaking, perhaps a few 100 million years. During that time, the core will heat enough to begin fusing helium into carbon and oxygen. But helium fusion produces less energy than hydrogen fusion. The core will continue to contract, and eventually, fusion will cease entirely. The outer layers will drift away, forming a glowing shell of gas called a planetary nebula. Beautiful structures, often symmetrical, lit from within by the hot core of the dying star. And at the center, the core itself will remain, no longer fusing, no longer generating energy, just slowly cooling. This remnant is called a white dwarf. It's incredibly dense, about the size of Earth but with the mass of the sun. A teaspoon of white dwarf material would weigh tons. White dwarfs don't burn. They simply radiate the heat they have left, fading slowly over billions of years. Eventually, they will cool to the point where they no longer emit visible light. They'll become black dwarfs, dark and cold, effectively invisible. But the universe isn't old enough yet for any black dwarfs to exist. Even the oldest white dwarfs, the remnants of stars that formed billions of years ago, are still faintly glowing. More massive stars meet different fates. When a star much larger than the sun exhausts its fuel, it doesn't stop at fusing helium. It continues, building heavier and heavier elements in its core. Helium fuses into carbon, carbon into neon, neon into oxygen, oxygen into silicon, silicon into iron. Each step requires higher temperatures and pressures. Each step produces less energy than the one before. The star is racing through its fuel at an accelerating pace. When the core fills with iron, fusion stops. Iron won't fuse into heavier elements without consuming energy rather than releasing it. The process that powered the star for millions of years comes to an abrupt halt. And without fusion, there's nothing to support the core against its own gravity. The core collapses. In less than a second, it shrinks from the size of Earth to the size of a city. Protons and electrons are crushed together, forming neutrons. The core becomes a neutron star, an object so dense that a teaspoon of its material would weigh as much as a mountain. The collapse releases an enormous amount of energy. The outer layers of the star, no longer supported, fall inward, then rebound off the incompressible neutron core. The star explodes. A supernova, one of the most energetic events in the universe. For a few weeks, a single supernova can outshine an entire galaxy. The explosion scatters the outer layers across space. All the elements forged in the star's core, and new elements created in the explosion itself, are dispersed into the surrounding gas. This enriched material will eventually be incorporated into new clouds, new stars, new planets. The cycle continues. Some of the heaviest elements, gold and platinum and uranium, are only created in these violent explosions or in the collisions of neutron stars. Every atom of gold that exists was forged in such an event. The neutron star left behind is bizarre. It spins rapidly, sometimes hundreds of times per second. Its magnetic field is trillions of times stronger than Earth's. If the magnetic field is aligned properly, the neutron star emits beams of radiation from its poles. As it spins, these beams sweep across space like a lighthouse. If one of the beams points toward Earth, we detect regular pulses. These objects are called pulsars. Neutron stars are stable as far as we know. They don't decay or evaporate. They just spin and cool, gradually slowing over millions of years. But if the collapsing core is massive enough, even neutrons can't resist gravity. The collapse continues past the neutron star stage. Nothing can stop it. The core shrinks to a point, or something so close to a point that the distinction doesn't matter. The density becomes infinite, or at least beyond anything physics can describe, and the gravity becomes so strong that not even light can escape. The object becomes a black hole. The boundary around a black hole, the point of no return, is called the event horizon. Cross that boundary, and every path leads inward. There's no escape, not because something is pulling you in, exactly, but because space-time itself is so warped that all future directions point toward the center. From the outside, black holes are invisible. They don't emit light. They don't reflect light. They're perfectly black, but they're not completely undetectable. Matter falling toward a black hole heats up, glowing brightly before it crosses the event horizon. And black holes have gravity, which affects the motion of nearby objects. By watching how stars move near the centers of galaxies, astronomers have found supermassive black holes, millions or billions of times the mass of the Sun, sitting at the galactic core. Nearly every large galaxy seems to have one. Our own Milky Way has a supermassive black hole at its center, about 4 million times the mass of the Sun. These black holes didn't form from a single collapsing star. They grew over time, accumulating mass from gas, dust, and stars that ventured too close. Some may have formed from the collapse of massive gas clouds in the early universe. Black holes can merge. When two galaxies collide, their central black holes eventually spiral together, releasing gravitational waves as they merge into a single larger black hole. Gravitational waves are ripples in space-time itself, traveling at the speed of light, predicted by Einstein's general relativity but only recently detected directly. When black holes merge, they shake space-time violently. Those ripples spread across the universe, carrying information about the collision. On Earth, we've built detectors sensitive enough to measure these waves, laser interferometers, kilometers long, capable of detecting changes in length smaller than a proton's width. The discovery of gravitational waves opened a new way of observing the universe, not through light, but through the vibrations of space-time itself. Black holes are strange objects. They represent the ultimate victory of gravity over all other forces. Matter compressed beyond the point where any known physics can describe it, and they may not be eternal. Stephen Hawking showed that black holes can emit radiation very slowly through quantum effects near the event horizon. Pairs of particles spontaneously appear and disappear in empty space all the time, a consequence of quantum mechanics. Near a black hole's event horizon, one particle of a pair might fall in while the other escapes. To an outside observer, it looks like the black hole is emitting particles. This is called Hawking radiation. The effect is incredibly weak. For a black hole the mass of the Sun, the temperature of Hawking radiation would be far colder than the cosmic microwave background. The black hole would absorb more radiation than it emits, but over time, unimaginably long time, black holes will gradually lose mass through Hawking radiation. Smaller black holes radiate faster. As a black hole shrinks, it radiates more and more quickly, eventually evaporating entirely. A solar mass black hole would take something like 10 to the 67th power years to evaporate. A supermassive black hole would take even longer. But given enough time, even black holes fade. Nothing in the universe, it seems, is truly permanent, while stars are born and die. While black holes form and slowly evaporate, galaxies continue to evolve. They collide and merge. When two galaxies pass close to each other, their mutual gravity distorts them, pulling out long streamers of stars and gas. Sometimes they merge entirely, their stars mingling, their gas clouds colliding and triggering bursts of new star formation. Our own Milky Way is on a collision course with the Andromeda Galaxy, our nearest large neighbor. In about 4 billion years, the two will begin to merge. The collision won't be violent, exactly. Galaxies are mostly empty space. Stars are so far apart that actual collisions between stars will be rare, but the gravitational interactions will reshape both galaxies. They'll lose their spiral structure, merging into a single elliptical galaxy. This has happened countless times throughout the universe. Many of the elliptical galaxies we see are the products of past mergers. Galaxy mergers can also feed the supermassive black holes at galactic centers. Gas funneled inward by the gravitational chaos provides fuel for the black hole to consume. When a supermassive black hole actively consumes material, it becomes incredibly bright. The infalling matter forms an accretion disk, a swirling disk of gas heated to millions of degrees. The energy released can outshine the entire galaxy. These objects are called active galactic nuclei, or quasars when especially bright. Quasars were more common in the early universe. We see them at great distances, which means we're seeing them as they were billions of years ago, when galaxies were younger and more gas-rich. Today, most supermassive black holes are quiet, dormant. They've consumed most of the available gas in their vicinity. Ours is quiet. It occasionally snacks on a passing gas cloud or star, but it's not actively feeding between the galaxies. In the vast spaces that separate them, there's not quite nothing. Intergalactic space contains gas, very thin, just a few atoms per cubic meter. Far more diffused than the best vacuum we can create in a laboratory. But over the vast volumes of space, even such thin gas adds up. There's more matter between galaxies than within them. This intergalactic medium is mostly hydrogen, left over from the Big Bang. Some of it is neutral, some ionized. It's difficult to observe directly. It doesn't emit much light, but it absorbs light from distant quasars, leaving characteristic signatures in their spectra. By studying those absorption lines, astronomers can map the distribution of gas along the line of sight to distant quasars. They can trace the filaments of the cosmic web, the large-scale structure shaped by dark matter. The intergalactic medium is also enriched over time. Supernovae and galaxies eject gas into intergalactic space. Galactic winds, driven by intense star formation or active black holes, blow gas outward. So the space between galaxies isn't pristine primordial hydrogen. It's been polluted, in a sense, by the activity of galaxies. Traces of heavier elements, carbon and oxygen and iron, are present in the intergalactic medium. This cycling of matter from intergalactic space into galaxies, through stars, back out into intergalactic space, is ongoing. The universe is not static. It's constantly recycling its material. But over time, the rate of star formation is declining. Galaxies are running out of gas. Much of the available hydrogen has already been converted into stars. New stars are still forming, but at a slower rate than in the past. The peak of star formation in the universe occurred several billion years ago. Since then, the rate has been dropping. Eventually, star formation will cease almost entirely. galaxies will use up their gas reserves. What gas remains will be too diffuse, too hot, or too far from gravitational wells to collapse and form new stars. The universe will enter an era dominated not by young, bright stars, but by the remnants of old ones. White dwarfs, neutron stars, black holes. Galaxies will dim. The lights will go out, one by one. This won't happen soon, not for trillions of years. The universe is only about 14 billion years old now. It's still young, still active, still full of light, but the trend is clear. The universe is slowly winding down. The era of star formation, the era we live in, is temporary. And after it ends, after the last stars burn out, the universe will be a colder, darker, quieter place. But not completely empty, not completely still. Even in that distant future, things will happen, just more slowly, more subtly. White dwarfs will continue to cool. Neutron stars will continue to spin. Black holes will continue to evaporate, though at a rate so slow it's almost unimaginable. And the expansion of the universe will continue. Dark energy, that mysterious force, will keep pushing space apart. Galaxies that are not gravitationally bound to each other will drift farther and farther apart. Eventually, they'll move so far that light from one can no longer reach the other. The observable universe, from the perspective of any particular galaxy, will shrink. Only the galaxies in the local gravitationally bound group will remain visible. For the Milky Way, or rather for the merged galaxy, it will become after colliding with Andromeda. That means only a handful of nearby galaxies will remain in view. The rest of the universe will have receded beyond the cosmic horizon, carried away by the expansion of space. An observer in that far future would see a much emptier sky. Just a few dim galaxies nearby, and beyond them, nothing. No distant clusters, no cosmic web, just darkness. It would be easy to conclude that the universe consists only of those few visible galaxies, that nothing else exists, and in a sense, they'd be right. The rest of the universe would be causally disconnected. No information, no light, no influence of any kind could travel between the isolated island of galaxies and the rest of the cosmos. They would be alone. Not because other galaxies don't exist, but because the expansion of space has separated them beyond any possibility of contact. This is one vision of the far future. A universe fragmented into isolated pockets, each containing a handful of galaxies, each unaware of the others. Within each pocket, stars will have long since burned out. Only remnants will remain, and even those will slowly fade. White dwarfs will cool into black dwarfs, dark and invisible. Neutron stars will radiate away their remaining heat. Even black holes, over timescales that dwarf the current age of the universe, will evaporate. Eventually, after something like 10 to the 100 years, even the supermassive black holes at the centers of galaxies will be gone. And what will remain? Photons, stretched to enormous wavelengths by the expansion of space. Neutrinos drifting, perhaps a few stray electrons or positrons, and space itself still expanding, still dominated by dark energy. This endpoint is sometimes called heat death. The universe reaches a state of maximum entropy, where no energy gradients remain. No differences in temperature, no flows of heat, no motion, no change. Just a cold, dark, nearly empty expanse, expanding forever. It's a bleak picture, but it's based on the assumption that dark energy remains constant, that the laws of physics don't change, that no new processes emerge. And we can't be certain of any of those things. Dark energy might not be constant. It might weaken over time, allowing gravity to reassert itself. Or it might strengthen, tearing the universe apart in a big rip. Or perhaps the universe will undergo a phase transition, the way water freezes or steam condenses. The vacuum of space might suddenly shift to a lower energy state, and the laws of physics might change in ways we can't predict. Or maybe there are cycles. Maybe the universe expands, reaches some maximum size or state, then collapses back, only to expand again in a new Big Bang. This idea of a cyclic universe has been around for a long time. It appears in ancient philosophies, in myths and religious traditions. The eternal return, the wheel of time, creation and destruction repeating endlessly. Modern physics doesn't rule it out. There are models, speculative but mathematically consistent, in which the universe bounces. The Big Bang wasn't the beginning, but a transition from a previous contracting phase. In these models, the universe breathes, expanding, contracting, expanding again. Each cycle might last trillions of years, but the pattern repeats. Whether this is true, we don't know. It's difficult to test. The conditions of a previous cycle, if there was one, would likely be erased by the Big Bang, leaving no traces we could observe. But it's a possibility, a way the universe might avoid a final ending. Another speculative idea involves the multiverse. The notion that our universe is just one among many, perhaps infinitely many. In eternal inflation, the process that may have caused our universe to expand so rapidly in its first moments, space is always inflating somewhere. Regions stop inflating and become universes like ours, but the process never ends globally. New universes are constantly bubbling into existence, each with potentially different properties, different constants of nature, different forces, different laws of physics. Our universe would be just one bubble in an infinite foam. Other bubbles would exist, but we could never observe them. They'd be forever beyond our reach, separated by inflating space. In this view, asking what came before the Big Bang, or what happens after the universe ends, becomes less meaningful. Our universe had a beginning, and it will have an end, but the larger multiverse has always existed, and always will. It's a mind-bending concept, and it's completely untestable with current technology. We can't observe other universes. We can't measure the properties of the multiverse as a whole, so it remains in the realm of speculation. Intriguing, mathematically plausible, but not part of established science. Still, these ideas point to something important: the limits of our knowledge. We can observe the universe back to the cosmic microwave background. We can infer conditions back to the blank time. We can project forward to the heat death or other far future scenarios. But we can't say with certainty what lies beyond those boundaries. What came before the Big Bang? What happens after the last star dies? There are gaps in our understanding, places where the data runs out, where the equations break down, where speculation takes over, and that's okay. Science doesn't claim to have all the answers. It's a process, ongoing, constantly refining and extending our knowledge. What we know about the universe today is vastly more than what we knew a century ago. And what we'll know a century from now will likely be even more. Perhaps future discoveries will answer the questions that seem unanswerable now. Perhaps new observations will reveal the nature of dark matter and dark energy. Perhaps a theory of quantum gravity will allow us to understand the Planck epoch. Or perhaps some mysteries will remain. Perhaps there are limits to what we can know. Fundamentally, not just practically. Either way, the journey of discovery continues. The universe keeps revealing its secrets, slowly, piece by piece. And as we learn more about the cosmos, we learn more about ourselves, about where we came from, what we're made of, how we fit into the larger picture. The atoms in our bodies were forged in stars. The elements that make up our cells, carbon and nitrogen and oxygen, were created in stellar cores and scattered by supernovae. We are, quite literally, made of stardust. Not metaphorically, but actually. The calcium in bones, the iron in blood, the phosphorus in DNA, all of it came from stars that lived and died long before the sun existed. And the energy that powers our bodies, the energy stored in the food we eat, traces back ultimately to the sun, which gets its energy from fusion, which releases energy that was stored in the hydrogen nuclei during the Big Bang. We are connected to the deepest past and the farthest reaches of the universe, not as separate observers but as participants, as part of the ongoing story. The universe doesn't have a purpose, as far as we can tell. It doesn't unfold according to a plan. It simply is, governed by physical laws, evolving according to those laws. But within that purposeless unfolding, complexity arises. Structure emerges. Stars form, planets coalesce, life appears, and with life, awareness. The capacity to observe, to wonder, to understand. The universe becomes conscious of itself in us. For a brief moment, in a small corner of space, matter has organized itself into forms that can contemplate the whole. It's a strange and beautiful thing that the cosmos, which began as a hot, dense, uniform state, would eventually produce beings capable of reconstructing that beginning. That the universe would give rise to minds that can trace its history, predict its future, ask what it means. We don't know if this has happened elsewhere, if other planets harbor life, if other civilizations have emerged and wondered the same things. The universe is vast. There are billions of galaxies, each with billions of stars, many with planets. The numbers suggest that life elsewhere is possible, maybe even probable, but we haven't found it yet. No signals from alien civilizations. No signs of life on other planets. Maybe we're alone, or maybe life is common, but intelligence is rare. Or maybe intelligence is common, but technological civilizations don't last long. Or maybe they're out there, but the distances are too great for communication. Space is so vast that even traveling at the speed of light, it would take years to reach the nearest stars. centuries to cross the galaxy. If civilizations exist on opposite sides of the galaxy, they might never know about each other. The signals would take too long to travel, and by the time a message arrived, the sender might be long gone. The universe is lonely in that way, vast and old and full of light, but separated by such immense distances that contact becomes impractical. Still, the search continues. Telescopes scan the skies for unusual signals. Probes explore the solar system, looking for signs of microbial life on Mars or the icy moons of Jupiter and Saturn. Each new exoplanet discovered is analyzed, its atmosphere studied for biosignatures, gases that might indicate the presence of life. So far, nothing. But the search is just beginning. We've only recently developed the tools to look, and the universe is patient. Perhaps one day, we'll find an answer. Perhaps we'll discover that life is everywhere, common and resilient, adapting to every environment. Or perhaps we'll find that we're unique, alone in a vast and empty cosmos. Either answer would be profound, either would change how we see ourselves. For now, we continue to wonder, to look outward, to ask questions, and the universe, indifferent and magnificent, continues its slow evolution. Stars burning, galaxies turning, space expanding, carrying everything gently, inexorably, toward whatever future awaits. The story isn't over. It's still being written, and we're part of it, however briefly, however small our role. Made of atoms from ancient stars, powered by energy from the Big Bang, conscious for a fleeting moment in cosmic time, watching the night sky, tracing the paths of planets, measuring the distances to galaxies, trying to understand, not because we need to, not because understanding changes anything fundamental, but because something in us wants to know. Something in us reaches outward, toward the stars, toward the beginning, toward the unknown. And in that reaching, we're doing what the universe has always done. Unfolding, exploring, becoming more complex, more aware, more connected. Questions that may never have answers. To look outward and see not just distant lights, but the history of everything woven into their glow. The universe doesn't ask questions about itself. Stars don't wonder where they came from. Galaxies don't contemplate their fate. Black holes don't ponder the nature of space-time. Only here, on this small world, in minds built from atoms that once drifted through interstellar space, does the cosmos turn its attention inward, reflecting on its own existence. And perhaps that's the strangest thing of all, not the Big Bang or inflation or dark energy, but the fact that awareness emerged at all, that the universe produced something capable of understanding it, even partially. Consciousness is a mystery in its own right. Not a cosmological mystery, but a biological and philosophical one. How does matter become aware? How do neurons firing in precise patterns give rise to subjective experience? We don't fully know. We can trace the physical processes, signals traveling along nerve cells, chemicals crossing synapses, patterns of electrical activity in the brain. But the felt quality of experience, the redness of red, the sensation of warmth, the thought of a thought, these don't obviously emerge from physics alone. Yet they must, because because we exist. Because consciousness arose through natural processes, through evolution, through the organization of matter into ever more complex forms. Life itself is a kind of complexity, emerging from simpler rules. Molecules that can replicate themselves, that can evolve, that can adapt to their environment. It began, as far as we can tell, with simple chemistry. Organic molecules forming in water, perhaps in tidal pools or deep sea vents. Amino acids, nucleotides, lipids, the building blocks of life. These molecules can form spontaneously under the right conditions. We found them in meteorites, in interstellar clouds, even synthesized them in laboratory experiments, simulating early Earth conditions. At some point, some combination of molecules became able to copy itself. Not perfectly, but well enough. And when copies are imperfect, variation arises. And when there's variation, natural selection begins. Molecules that copied themselves more efficiently became more common. Molecules that were more stable lasted longer. Over time, complexity increased. Chains of molecules formed. RNA, perhaps, capable of both storing information and catalyzing reactions. A molecule that could serve as both blueprint and machine. Eventually, these molecular systems became enclosed in membranes, forming the first cells. Simple at first, just a membrane and some self-replicating molecules inside. But over time, evolution produced more complex cells. Cells with specialized structures, with ways to harvest energy from their environment, with increasingly sophisticated chemistry. And eventually, some cells learned to work together. Colonies formed. Specialization occurred. Some cells became better at one task, others at another. This cooperation led to multicellular life. Organisms made of many cells, each contributing to the whole. Plants, animals, fungi, all built on this principle. With multicellularity came new possibilities. Size, for one. Single cells are limited by surface area to volume ratios, but multicellular organisms can grow large. And with size came complexity, specialized tissues, organs, systems, a division of labor that allowed for more sophisticated responses to the environment. Nervous systems emerged. Cells specialized for transmitting signals, for sensing the environment, for coordinating responses. Simple at first, just a network of nerve cells. But over hundreds of millions of years, nervous systems became more elaborate. Ganglia formed, concentrations of nerve cells, then brains, centralized processing centers. And with brains came behavior. Not just reflexive responses, but something more flexible. Memory, learning, the ability to change behavior based on experience. Eventually, in some lineages, something like consciousness appeared. Subjective experience. Awareness not just of the environment, but of the self. We don't know exactly when or how this happened. Consciousness doesn't fossilize. We can't point to a specific moment and say, here, this is where awareness began, but it happened. And in at least one species, it became sophisticated enough to reflect on its own existence, to wonder about the universe, to ask where it all came from. That species looks up at the night sky and sees not just lights, but other suns, other worlds, a history stretching back billions of years. And in trying to understand that history, in piecing together the story of the cosmos from scattered clues, that species participates in something profound, the universe examining itself. Matter organized in such a way that it can contemplate matter. It's a recursion, a loop. The cosmos giving rise to observers who observed the cosmos, who developed theories about how the cosmos gave rise to them. And those theories change how we see ourselves. Before we knew about the Big Bang, about the expansion of space, about the formation of stars and galaxies, the universe seemed static, eternal, unchanging. We seemed separate from it. Observers looking at a stage, not actors on it. But now we know we're part of the story. Not observers from outside, but patterns within the larger pattern. The distinction between us and the universe dissolves. We're not separate from it. We're continuous with it. Every breath is an exchange of atoms with the environment. Every thought is a cascade of chemical reactions. Every moment of awareness is a physical process. Neurons firing, patterns forming and dissolving. We're not things inside the universe. We're processes the universe is doing. Temporary, localized, brief, but real, and connected to everything else. The carbon in our bodies was forged in stars that died before the sun existed. The water we drink has cycled through clouds and oceans and living things for billions of years. We're built from recycled material, atoms that have been part of countless other structures, other forms, other lives. And when we die, those atoms will be recycled again, returned to the environment, incorporated into soil, into plants, into other organisms. Nothing is truly created or destroyed, just rearranged. Patterns forming, persisting for a time, then dissolving back into the larger flow. The universe is a vast process of transformation, energy flowing, matter organizing, complexity emerging and dissolving. Stars condense from gas clouds, burn for billions of years, then scatter their contents back into space. Planets form, evolve, eventually are consumed by their aging stars or flung into the void. Galaxies merge, their stars mingling, their black holes combining. Over time, the structures we see will change beyond recognition, but the underlying substance remains. Energy and matter, governed by physical laws, unfolding according to those laws. The laws themselves are interesting. Why these laws and not others? Why does gravity work the way it does? Why are there 4 fundamental forces and not 3 or 5? We don't know. The laws seem arbitrary, in a sense. We can describe them mathematically. We can measure the constants that appear in the equations, but we can't explain why those particular values. Change the strength of gravity by a small amount, and stars wouldn't form. Change the mass of the electron, and atoms would be unstable. Change the strength of the strong nuclear force, and nuclei wouldn't hold together. The universe seems finely tuned for complexity, for the emergence of stars and planets, and eventually, life. This has led some to suggest that the universe was designed, that the constants were set deliberately to allow for our existence. But there's another explanation. If there are many universes, each with different constants, then it's not surprising we find ourselves in one where the constants allow for life. We couldn't exist in a universe where stars don't form or atoms don't hold together. So naturally, we find ourselves in a universe where those things are possible. This is called the anthropic principle. Not that the universe was designed for us, but that we necessarily find ourselves in a universe compatible with our existence. It's a kind of selection effect. We observe the universe that allows observers to exist, because we couldn't exist in any other kind. Whether there actually are other universes with different laws is unknown. It's not something we can test directly, but it's a logical possibility. And it removes the need for fine-tuning to seem mysterious. If there are countless universes with all possible combinations of constants, then some will inevitably have the right conditions for complexity. We happen to be in one of those. Not because it was designed, but because those are the only universes where observers can arise to ask the question. It's a strange kind of reasoning. Circular, almost. But it makes a certain sense. Still, it leaves deeper questions unanswered. Why are there any universes at all? Why does anything exist rather than nothing? These questions may be beyond the reach of science. Science explains how things work, how they change, how they relate to each other, but it doesn't explain why there's something rather than nothing. That may be a question without an answer, or a question that doesn't quite make sense, like asking what's north of the North Pole. Existence may simply be a brute fact, something that just is, without explanation or justification. And if that's the case, then all we can do is explore it, map its features, trace its history, understand its workings, which is what we've been doing. Looking back through time, from the present to the formation of stars and galaxies, to the cosmic dark ages, to recombination and the cosmic microwave background, to nucleosynthesis, to inflation, to the Planck epoch. Each step takes us closer to the beginning, but the beginning itself remains elusive, hidden behind the horizon of what we can observe or calculate. Perhaps it will always remain hidden. Perhaps there are limits to what we can know, not just practical limits, but fundamental ones. Or perhaps future discoveries will reveal more. Perhaps a theory of quantum gravity will allow us to understand the Planck epoch. Perhaps new observations will show us what lies beyond the cosmic microwave background. The history of science is full of surprises. Things that seemed impossible to know, like the composition of stars or the age of the universe, turned out to be knowable with the right tools and methods. So it's premature to say we've reached the limits. There may be much more to discover. For now, though, we've traced the story as far as current understanding allows. From the earliest describable moments to the present, and beyond into possible futures, the universe began. Or at least our observable portion of it began. In a hot, dense state, it expanded and cooled. Forces separated, particles formed, nuclei assembled, atoms combined, light was freed. The cosmic dark ages followed, stars ignited, galaxies coalesced, elements were forged and scattered, planets formed, life emerged. Now, billions of years later, here we are. Conscious, curious, trying to understand. The future is less certain. The expansion continues, accelerating under the influence of dark energy. Stars will keep forming for a while, but the rate is declining. Eventually, in trillions of years, star formation will cease. The universe will enter an era of remnants. White dwarfs, neutron stars, black holes, and eventually, even those will fade. White dwarfs will cool. Black holes will evaporate. The universe will approach a state of maximum entropy, or perhaps something else will happen, a phase transition, a collapse and rebound, a branching into new regions of a multiverse. We don't know. The far future is as mysterious as the deep past, but that's part of the beauty. The universe is vast and old and full of unknowns. Despite everything we've learned, there's so much more we don't understand. Dark matter, dark energy, the nature of quantum gravity, the origin of the matter-antimatter asymmetry, the possibility of other universes, the question of whether we're alone. Each mystery is an invitation, a prompt to keep looking, keep questioning, keep exploring. And in the meantime, we have this moment, this brief flicker of awareness in the long cosmic night, stars shining overhead, galaxies turning slowly in the dark, the cosmic microwave background whispering across space, carrying news of the ancient past, all of it connected. All of it part of a single unfolding story, not a story with a clear beginning or a definite ending, not a story with a moral or a purpose, just a story of change, of transformation, of complexity emerging from simplicity and dissolving back into it, a story we're part of, whether we understand it or not. The atoms in our bodies have been cycling through the cosmos for billions of years. They've been part of stars, part of interstellar clouds, part of planets and asteroids. They've been through countless configurations, countless forms. And now, for a brief time, they're arranged in a pattern that can think, that can wonder, that can look back and trace their own history. It won't last. Eventually, the pattern will dissolve. The atoms will scatter, be incorporated into other structures, other lives, other processes. But for now, it exists. This temporary arrangement of matter that calls itself a person, that experiences the world, that thinks about the universe. And that's enough. Not permanent, but real. Not eternal, but present. The universe doesn't care. It continues regardless, indifferent to the small patterns that arise and dissolve within it. But the patterns care. They care about themselves, about each other, about the larger whole they're part of. And in that caring, in that awareness, something meaningful emerges. Not objectively, not cosmically, but subjectively, locally. In the experience of the pattern itself. Meaning doesn't have to be cosmic to be real. It doesn't have to be eternal to matter. It's enough that it exists now, in this moment, in this brief window of time, when the universe is the right age and temperature for life, for complexity, for consciousness. The window will close eventually. The universe will grow colder, darker, emptier. The conditions that allow for life will pass, but they're here now. And we're here now, part of the story, experiencing it from the inside, looking up at the night sky and seeing not just lights, but the history written in their glow. light from distant stars that traveled for years or centuries to reach us. The light from distant galaxies that left billions of years ago, when the universe was younger. Each photon carries information about the star that emitted it, about the space it traveled through, about the conditions along the way. By collecting and analyzing that light, we can reconstruct the past. We can see the universe as it was, trace its evolution, understand its structure, and we can project forward. Based on what we know, we can predict what will happen. Not with certainty, but with reasonable confidence. The sun will eventually become a red giant. The Milky Way will merge with Andromeda. Stars will continue to form, then eventually stop forming. The universe will expand forever, growing colder and darker. These predictions are based on our current understanding. They could be wrong. New discoveries could change the picture entirely, but they're the best we can do with what we know now. And they paint a picture of a universe that's temporary, dynamic, constantly changing. Nothing is permanent. Everything is in flux. Even the things that seem eternal, like stars and galaxies, are just temporary patterns, persisting for a time before dissolving, and that's okay. Impermanence isn't a tragedy. It's just the nature of things. The universe doesn't need to last forever to be worth experiencing. A sunset is beautiful even though it fades. A song is moving even though it ends. The same is true for existence itself. Brief, temporary, but real. And in that reality, there's something worth appreciating. The sheer improbability of being here at all. The vast chain of events, stretching back to the Big Bang, that led to this moment. If any one of countless factors had been different, we wouldn't exist. If the constants of nature were slightly different, stars wouldn't form. If the matter-antimatter asymmetry hadn't occurred, there would be no atoms. If the sun hadn't formed, or if Earth had formed in a different orbit, or if life hadn't emerged, or if evolution had taken a different path, we wouldn't be here. But all those things happened. A long chain of contingencies, each one necessary, each one unlikely. And here we are, the product of that chain. Temporary patterns of matter and energy, aware for a brief time, then gone, but present, real. Part of the universe in this moment, looking outward at the cosmos and inward at ourselves, and finding connections between the two. The carbon in our DNA from ancient stars, the energy in our cells from the sun, the atoms in our bones cycled through countless other forms. We're not separate from the universe. We're made of it. We're expressions of it. Temporary localized complexities in the larger flow. And in recognizing that, in understanding our place in the cosmic story, something shifts. The universe is no longer just out there, distant and separate. It's here, in us, looking at itself through our eyes. Every observation we make is the universe observing itself. Every thought we think is the universe thinking, not in some mystical sense, but literally. We are physical processes, arrangements of matter following physical laws. When we look at a star, photons travel from the star to our eyes, triggering chemical reactions in our retinas, sending signals to our brains. where patterns of neural activity give rise to the experience of seeing. All of that is physics, chemistry, biology, physical processes unfolding according to natural laws. And yet, it's also experience. Subjective, immediate, felt from the inside. The universe is both objective and subjective, both physical process and felt experience, both mechanism and meaning. And we're the place where those two aspects meet, where the objective universe becomes subjectively experienced. That's a strange and wonderful thing, and it's happening right now, in this moment. The act of reading these words, of thinking these thoughts, of feeling whatever feelings arise, all of it is the universe doing something, being something, experiencing something, not everywhere, not in stars or rocks or empty space, but here in this localized pattern of complexity. And that pattern won't last. Eventually, it will dissolve. The neurons will stop firing. The body will decay. The atoms will be recycled. But for now, it's here, this moment of awareness, this brief window of consciousness, this temporary vantage point on the cosmos. And from this vantage point, the universe looks a certain way. Not the way it looks from other vantage points. Not the way it is objectively, but the way it appears to this particular arrangement of matter. That appearance is real, even if it's not the whole picture, even if it's just one perspective among countless others. The universe contains multitudes, countless perspectives, countless experiences, countless ways of being. Most of those perspectives are simpler than ours. A bacterium's experience of the world, if it has one, is probably very different from ours. A tree's interaction with its environment isn't accompanied by self-awareness, but they're all part of the same process. All expressions of matter organizing itself, responding to its environment, persisting through time. And maybe, elsewhere in the universe, there are other complex perspectives, other arrangements of matter that have become self-aware, other beings looking up at their own night sky, wondering if they're alone, trying to understand the cosmos they find themselves in. We don't know. We've looked, but we haven't found anyone yet. The universe is vast and mostly empty. Even if life is common, the distances are so great that contact might be impossible, but the possibility remains. Somewhere on some other world orbiting some other star, there might be others asking the same questions. Where did we come from? Why are we here? What happens next? Questions that arise naturally when complexity becomes self-aware. When the universe develops the capacity to wonder about itself, these questions don't have simple answers. Some don't have answers at all. But the asking itself is significant. It means something has changed in the universe. Something new has emerged, not just matter, not just energy, but meaning. Purpose, even if only local and temporary. Value, even if only subjective. The universe doesn't have meaning in itself. It just is, unfolding according to physical laws, indifferent to outcomes. But within the universe, in small pockets of complexity, meaning arises. Not imposed from outside, but generated from within. We care about things, we value things. We find some outcomes better than others, some experiences more worthwhile. That caring, that value valuing is real. It's a physical process, patterns of neural activity, but it's also something more, something that can't be fully captured by descriptions of neurons firing. It's what it's like to be this pattern. The subjective quality of experience. And that quality matters, at least to the pattern experiencing it. The universe as a whole might not care, but the localized complexities within it do, and that's enough. We don't need cosmic significance to justify our existence. We don't need the universe to have a purpose for our lives to have meaning. The meaning is here, in the experience itself, in the caring and valuing and wondering that arise naturally in complex self-aware systems. And for a time, however brief, that meaning is real, present, actual. The universe brought it into being through a long process of cooling and condensing and organizing. And eventually, the universe will dissolve it back into simpler forms. But in between, there's this moment of awareness, this capacity to wonder, this ability to look back at the history of everything and forward toward possible futures. It's a gift, in a sense, not given by anyone, but arising naturally from the way the universe works. Complexity emerging from simplicity. Awareness emerging from matter. Meaning emerging from physical process. All of it temporary, contingent, fragile, but real. And as the thoughts drift, as awareness softens and blurs, as the boundaries between self and universe become less distinct, there's a kind of peace in that recognition, not separate, not isolated, but continuous with everything, part of the larger flow. Atoms that were once in stars, now briefly arranged into this form, soon to scatter and become something else. Energy that flowed from the Big Bang through countless transformations, now powering these thoughts, these feelings, this moment of awareness. And when this particular pattern dissolves, the atoms will remain. The energy will continue, just in different configurations, different forms. Nothing truly lost, nothing truly gained. Just transformation, endless transformation, the universe rearranging itself moment by moment. And somewhere in that vast process, for a brief time, a pattern emerged that could think about it all, could wonder, could look back through billions of years and see where it came from. That pattern is here now, aware, awake, thinking these thoughts, feeling whatever arises in this moment. And soon, perhaps very soon, that pattern will dissolve into sleep, into unconsciousness, into a temporary cessation of awareness. And in that dissolution, there's no tragedy, just rest, a pause in the ongoing process, the universe continuing without this particular perspective, until the pattern reforms and awareness returns. For now, though, the thoughts drift slowly outward, like light from a distant star, traveling through space, carrying information about something that once was, that once shone brightly for a time, the universe vast and old, full of light and darkness, full of patterns forming and dissolving, full of complexity and simplicity, full of everything and nothing. And this small awareness, this temporary vantage point, settling gently back into the larger whole from which it briefly emerged, dissolving like mist in morning light. Sleep is a kind of small death, a temporary letting go of awareness, of the boundaries that separate self from world. In sleep, the patterns that create consciousness loosen, drift apart, reform in strange configurations that we call dream. And in dreams, the rules change. Time becomes fluid. Impossible things happen without seeming strange. The mind, freed from the constraints of waking logic, wanders through landscapes that never existed but feel somehow familiar. Perhaps the universe dreams too, in its own way. Not consciously, not with intention, but through the endless variations it generates. Each galaxy a different configuration, each star a different possibility, each planet a different experiment in what matter can become. Some of those experiments produce nothing interesting. Rocky worlds with no atmosphere, orbiting too close to their stars or too far away. Gas giants with nothing but hydrogen and helium, no solid surface, no complexity. But some experiments produce something more. Liquid water, complex chemistry, the gradual emergence of self-replicating molecules, and on at least one world, perhaps on many, those experiments led to life, to complexity that sustains itself, that adapts, that evolves. Evolution has no direction, no goal. It's not trying to produce anything in particular. It's just the inevitable consequence of reproduction with variation in an environment with limited resources. Organisms that reproduce more successfully become more common. That's all. No purpose, no design, just differential reproduction over time. And yet, from that simple process, extraordinary complexity emerges. Eyes that can see, ears that can hear, brains that can think. None of it planned. All of it the result of countless small variations, most of which failed, a few of which succeeded and propagated. Over billions of years, that process produced organisms of staggering sophistication. Cells with specialized structures, bodies with specialized organs, nervous systems that can process vast amounts of information. And eventually, in at least one lineage, something like consciousness arose. The capacity not just to respond to stimuli, but to experience them, to feel, to be aware. We don't know if other animals are conscious in the way we are. They behave as if they have experiences, as if they feel pain and pleasure, as if there's something it's like to be them, but we can't know for certain. Consciousness doesn't leave traces. We can only infer it from behavior, from neural structure, from similarities to ourselves. The dog seems conscious. It responds to its name. It learns. It appears to have emotions. But is there really something it's like to be a dog? Or is it just complex behavior, sophisticated but unconscious processing? We don't know. And for simpler organisms, the question becomes even more uncertain. Is there something it's like to be a fish, a bee, an ant? At what point does complexity give rise to experience? Or is experience present in some form all the way down, in simpler and simpler versions, until it fades into something we wouldn't recognize as consciousness at all? These questions don't have clear answers. They're at the boundary between science and philosophy, where empirical observation meets questions that can't be fully resolved by observation alone. But they matter, in a way, because how we answer them affects how we see ourselves, how we relate to other living things, how we understand our place in the larger pattern. If consciousness is unique to humans, then we're fundamentally separate from the rest of nature. Special, different, alone in our awareness. But if consciousness is widespread, present in many forms throughout the living world, then we're just one variation on a theme. More complex, perhaps, but not different in kind. The evidence suggests the latter. Our brains aren't fundamentally different from other mammalian brains. The same structures, the same neurotransmitters, the same basic mechanisms. The differences are mostly quantitative. We have larger prefrontal cortexes, more complex language abilities, more sophisticated social cognition, but the building blocks are the same. And if our consciousness arises from neural activity, then it seems likely that other animals with similar neural structures have similar experiences, different in detail perhaps. A bat's echolocation creates a sensory experience we can't imagine. A bird's visual system sees colors we can't perceive, but experience nonetheless. Awareness of some kind, however different from ours. And if experience is that widespread, if it's a natural consequence of certain kinds of information processing, then perhaps it's not as special as we thought. Perhaps the universe is full of perspectives. Not just human perspectives, not just animal perspectives, but countless ways of experiencing, most of them utterly alien to us. That's speculation. But it's grounded in what we know about how consciousness relates to physical systems. Awareness seems to arise when information is integrated in certain ways. When a system has enough complexity, enough feedback loops, enough capacity to model itself and its environment. The threshold isn't clear, but it exists somewhere, and many organisms seem to cross it, which means we're not alone, even on this one planet. We're surrounded by other experiencing beings, other perspectives, other ways the universe is aware of itself. That's both humbling and comforting. Humbling because it means we're not as unique as we might like to think. Comforting because it means we're not as isolated. The same processes that gave rise to our awareness gave rise to theirs. We're all expressions of the same underlying reality, different configurations of matter and energy, but fundamentally connected. And that connection extends beyond living things. The atoms in our bodies have been part of countless other structures. The water we drink has been part of ancient oceans, has fallen as rain on mountains that no longer exist, has flowed through rivers long since dried up. Everything is recycled. Nothing is truly new, just rearranged. The universe is a vast recycling process. Matter flowing from one configuration to another, never created, never destroyed, just transformed. Stars condense from diffuse gas. They burn for billions of years, fusing hydrogen into helium, helium into carbon, carbon into heavier elements. Eventually they die, returning their material to space. That material becomes part of new clouds, new stars, new planets. The cycle continues, has continued for billions of years, will continue for billions more, until eventually, in the far future, the fuel runs out. No more gas to form stars, no more fusion to create light and heat. The universe will enter a quieter era, an age age of remnants and slow decay. White dwarfs will cool gradually, radiating their stored heat into the expanding void. Neutron stars will spin silently in the dark, their rotation gradually slowing over eons. Black holes will sit quietly, occasionally consuming whatever matter drifts too close, but mostly just existing, warping space-time around themselves, and the expansion will continue. Dark energy pushing space apart, thinning the universe, increasing the distance between everything. Eventually, even gravitationally bound structures might be affected. If dark energy strengthens over time, it could overcome the gravity holding galaxies together. First, galaxy clusters would disperse. Then, individual galaxies would begin to tear apart. Stars would be flung into intergalactic space, and if the acceleration continued, even stars would be disrupted. Planets pulled away from their orbits. Moons separated from their planets. Eventually, even atoms might be torn apart. The electromagnetic force holding electrons to nuclei overcome by the expansion of space itself. This is the Big Rip scenario. An ending where the universe doesn't fade quietly but tears itself apart, piece by piece, until nothing remains but isolated subatomic particles, unable to interact, separated by vast distances. It's a dramatic ending, but it's just one possibility, and probably not the most likely one. More likely, dark energy will remain constant or weaken slightly. The expansion will continue, but structures held together by gravity will remain intact. Galaxies, or at least the merged remnants of galaxies, will persist. Isolated islands in an expanding void. And within those islands, the slow process of decay will continue. Stars burning out, white dwarfs cooling, black holes evaporating incredibly slowly through Hawking radiation. After timescales almost impossible to comprehend, even the black holes will be gone. Evaporated completely, their mass converted into radiation and scattered across space. And what remains will be a cold, dark, nearly empty universe. Photons with wavelengths longer than galaxies. Occasional particles separated by vast distances. And space itself still expanding, still dominated by dark energy. This is heat death. The universe reaching a state of maximum entropy, where no energy differences remain, where nothing can happen because everything is already in equilibrium. It's a quiet ending. Not dramatic, just the slow running down of all processes. The gradual dissipation of all structure, until nothing is left but uniformity. From a human perspective, it seems bleak. The end of everything, the final dissolution of all complexity. But from the universe's perspective, if it had one, it's just another state. Not better or worse than any other, just different. And it's so far in the future that it's almost meaningless to think about. Timescales measured in 10 to the 100 years or more. Longer than the current age of the universe by factors that dwarf imagination. By comparison, the time that life has existed on Earth, a few billion years, is less than a blink. The time that complex life has existed, a few 100 million years, is even shorter. The time that humans have existed, a few 100,000 years, is infinitesimal, and the time that human civilization has existed, a few thousand years, barely registers. We live in a very specific moment, a brief window when the universe is the right age and temperature for complexity, for life, for consciousness. Before this window, the universe was too hot, too dense, too uniform. Stars hadn't formed yet, galaxies didn't exist. There was nowhere for life to emerge. After this window, the universe will be too cold, too empty, too dispersed. Stars will have burned out. Galaxies will be isolated. There will be no energy sources to sustain complexity. But now, in this moment, conditions are right. Stars shine, planets orbit, life exists, and occasionally, life becomes aware of itself, looks around, and wonders. It's a privileged moment, in that sense. Not designed, not intended, but fortuitous. A brief period when the universe is capable of knowing itself, and we're here for it, part of it, experiencing it from the inside. That won't last. Our species will end eventually. Maybe in a few thousand years, maybe in a few million. But eventually, and long before the universe reaches heat death, long before the last stars burn out, humanity will be gone. Either extinct or evolved into something else. Something we wouldn't recognize as human. But for now, we're here, aware, capable of understanding, at least partially, the vast story we're embedded in, from the Big Bang to the present, from the first particles to the first atoms, to the first stars, to the first galaxies, to the first planets, to the first consciousness. A chain of events stretching across billions of years, each one necessary for the next, each one contingent and unlikely. And here we are at one particular link in that chain, not the end, because the story continues beyond us. But a significant moment nonetheless, the moment when the universe developed the capacity to reflect on its own history, to trace the path from beginning to present, to project forward into possible futures. That capacity is fragile. It depends on brains, which depend on bodies, which depend on planets, which depend on stars, which depend on galaxies. Remove any link in that chain and the capacity disappears. No stars, no heavy elements. No heavy elements, no rocky planets. No planets, no stable environments. No stable environments, no life. No life, no consciousness. The whole edifice is built on foundations that could easily have been different. If the constants of nature were slightly different, stars might not form. If the matter-antimatter asymmetry hadn't occurred, there would be no atoms. If the solar system had formed slightly differently, Earth might be too hot or too cold for liquid water. If the moon didn't exist, Earth's rotation would be unstable, its climate chaotic. So many things had to be just right. Not perfectly right, but within certain ranges. And they were. Not because of design, not because of intention, but because out of all the possible universes, all the possible configurations, we find ourselves in one where those conditions are met. We couldn't exist in any other kind, so naturally we exist in this kind. The anthropic principle again. Not an explanation exactly, but a recognition that our existence filters which universe we observe, and the universe we observe is one capable of producing observers, complex enough for stars and galaxies, stable enough for planets and chemistry, old enough for evolution to produce intelligence. A universe in its middle age, neither too young nor too old, neither too hot nor too cold. The universe, in other words, very much like the one we see, because that's the only kind we could see. And what we see is beautiful in its own way, not designed for beauty, not arranged for aesthetic purposes, but beautiful nonetheless. The spiral arms of galaxies, the delicate tracery of nebulas, the stark brilliance of stars against the dark. These are patterns that emerged naturally from physical laws, gravity, electromagnetism, quantum mechanics, all working together to create structure. No artist designed them. No intelligence arranged them. They simply are the inevitable result of matter and energy, following the rules that govern them. And yet, they move us. They inspire awe, wonder, curiosity, not because they were made for us, but because we've evolved to appreciate pattern, to respond to beauty, to find meaning in structure. Our brains are pattern recognition machines. That's what they evolved to do. Recognize patterns in the environment, predict what will happen next, respond accordingly. And that same machinery, developed for survival, now responds to the patterns in the cosmos, sees beauty in galaxies, elegance in physical laws, meaning in the vast sweep of cosmic history. It's a side effect, in a sense. The universe didn't evolve our aesthetic sense. Evolution did, for practical purposes. But the result is that we can appreciate the universe in ways that go beyond survival. We can find it beautiful, meaningful, worthy of contemplation. And in that contemplation, something happens. The boundary between observer and observed blurs. The separation between self and cosmos becomes less distinct. We're not outside the universe looking in. We're inside, part of it, made of the same stuff, following the same laws. When we look at stars, we're looking at the source of our own atoms. When we think about the Big Bang, we're thinking about our own origin. The universe isn't something separate from us. It's what we are. We're localized patterns of complexity within it, temporary arrangements that have become self-aware. And in that self-awareness, the universe becomes aware of itself. Not everywhere, not completely, but in small pockets scattered through space and time. Here, now, in this moment, in this particular arrangement of atoms that can think and feel and wonder, it's happening right now. The universe contemplating itself through eyes that are made of stardust, through thoughts that are patterns of neural activity, through awareness that arose from billions of years of evolution, all of it physical, all of it natural, all of it part of the larger pattern. And as awareness softens, as thoughts become slower and less distinct, as the boundaries blur further and the sense of separation fades, there's a return to something simpler. Not unconsciousness exactly, not yet, but a state where the active mind quiets, where the constant stream of thoughts slows to a trickle, where awareness becomes more diffuse, less focused. This is the edge of sleep, the threshold between waking and dreaming, a liminal space where the rules are unclear, where the sense of self becomes negotiable. In this space, thoughts drift without direction. Memories surface without context. Images appear and dissolve without narrative. The mind, freed from the task of making sense of the world, simply wanders, following associative chains, making connections that would seem strange in waking consciousness. This is where creativity lives, where novel combinations arise, where ideas that seemed unrelated suddenly merge into new patterns. Scientists and artists often report that their best insights come not during focused work, but during these in-between moments. Half asleep, daydreaming, letting the mind wander without goal or structure. Perhaps because in these states, the usual filters are relaxed. The brain's default mode network activates, making connections across domains, finding patterns that focused attention would miss. The universe might work the same way, metaphorically, not thinking or planning, but exploring possibility space, trying endless combinations, most of which lead nowhere, a few of which produce something interesting. Stars forming and dying, galaxies colliding and merging, planets condensing from dust and gas, life emerging and evolving, all of it exploration without purpose. The universe trying things out, not because it's looking for anything in particular, but because that's what it does. It unfolds, it varies, it generates possibility, and occasionally, very occasionally, something remarkable emerges. A planet with the right conditions for life. A species with the capacity for awareness. A moment when the universe becomes conscious of itself. These moments are rare, brief, scattered across vast reaches of space and time. But they're real. They exist. And in existing, they add something to the universe that wouldn't be there otherwise. Not objectively better, not cosmically significant, just different. A new way of being, a new pattern, a new perspective on the whole. And from that perspective, the universe looks a certain way, feels a certain way, means something, even if that meaning is local and temporary. The meaning doesn't have to be eternal to be real. It doesn't have to be universal to matter. It's enough that it exists now, in this moment, in this particular arrangement of matter that has become aware. And as that awareness fades, as sleep approaches, as consciousness dissolves into simpler patterns, there's no loss. Just transformation. The atoms remain. The energy continues. The patterns change, but nothing is destroyed. Sleep is a small preview of death. A temporary dissolution. A letting go. A return to something less structured, less defined. And in sleep, there's rest. A pause in the constant activity of consciousness. A chance for the system to reset, to repair, to prepare for another cycle. The universe doesn't sleep, but it has its own cycles. Stars are born and die. Galaxies form and merge. The expansion continues, the cooling proceeds, structures emerge and eventually dissolve. Everything in motion, everything changing, everything flowing from one state to another. And in that flow, temporary patterns arise. Vortices in the stream. Eddies that persist for a while, then merge back into the current. Consciousness is one such pattern. arising from the flow, existing within it, eventually dissolving back into it. But while it exists, it experiences, it knows. It participates in the universe's ongoing exploration of what's possible, and that participation is its own justification, not leading anywhere, not serving any cosmic purpose, just being what it is. Awareness, experience, the universe knowing itself, briefly, locally, partially. In this moment, right now, that knowing is happening. These thoughts are the universe thinking. This awareness is the universe being aware. And as the thoughts slow, as awareness dims, as sleep approaches like a gentle tide, the universe continues. Not unchanged by this moment of consciousness, but not fundamentally altered either. Just one more pattern among countless others. One more way the universe explores itself. The stars still burn. The galaxies still turn. Space still expands. Dark energy still pushes everything apart. And somewhere, scattered across space and time, other patterns of consciousness arise. Other moments when the universe knows itself, other perspectives, other experiences, other ways of being, all temporary, all local, all part of the larger flow. Nothing permanent, but nothing truly lost either. Just transformation, endless transformation. The universe endlessly becoming something new while remaining fundamentally itself. And in that becoming, in that endless exploration of possibility, there's something like peace, not the peace of acceptance, of being what one is, of participating in the larger pattern without resistance. The universe doesn't struggle against itself. It simply unfolds, following the laws that govern it, exploring the possibilities those laws allow. And for a brief moment, part of that unfolding includes this awareness, this wondering, this contemplation of the whole, a moment that's already passing, already fading, already dissolving into sleep and dreams, and the quiet dark where consciousness rests between one day and the next. The universe vast and ancient, full of light and shadow, full of beginnings and endings that are also beginnings, full of patterns forming and dissolving in the endless dance of matter and energy and space-time itself. And this small awareness, this temporary knowing, settling back into the flow from which it emerged, not ending but transforming, not lost but changing form, becoming part of something larger again, part of the quiet dark between thoughts, part of the soft drift towards sleep, where dreams wait like distant galaxies, glowing faintly in spaces the waking mind can't quite reach. If you enjoyed this journey, please consider liking and subscribing to the Deep Somna, where curiosity meets calm every night. Sleep well, stay curious, and until next time, let the ocean's gentle embrace carry you peacefully